Question 1. So in variational autoencoders, the evidence lower bound can be written as the expected log likelihood minus the KL divergence regularizer. That is the first term, that is the reconstruction term. It measures how well we reconstruct the input, and the second term, that is the KL divergence term. It ensures that the latent space stays close to a known prior like a standard normal. So to the extension to diffusion models. So in diffusion models, there is although there's no encoder decoder pair, the likelihood is indirectly modeled through the reverse denoising process. The elbow in diffusion models appears when maximizing the data likelihood by summing over the denoising steps. Essentially a form of variational inference where the diffusion process defines the forward and reverse paths. So in both models, the elbow is crucial for learning a latent structure and generating new data by balancing fidelity and regularization. Question 2. So the standard VAE, it optimizes the evidence lower bound where the first term, that is the reconstruction loss, ensures that the generated data matches the input. So the beta VAE term modifies the elbow by introducing a hyperparameter that is called beta on the KL term. So the evidence lower bound becomes the reconstruction loss minus the beta times the KL divergence loss. So this beta is basically a tunable hyperparameter to control the strength of the KL divergence penalty. It can either be less than 1, more than 1, exactly 1, but it has to be greater than 0. So the effect of varying beta on latent representations. So like when beta becomes 1, it is the standard VAE objective. If the beta is greater than 1, we increase pressure on the latent posterior to align with the prior, and when beta is less than 1, we relax that constraint. So we allow more flexibility in encoding information. So if beta is less than 1, the reconstruction quality is high and there are richer latent encodings. But if the beta is greater than 1, it encourages disentanglement, leading to blurry reconstructions. Question 3. So diffusion models are based on a Markov process that gradually adds noise to data through many steps. This is called the forward diffusion process. So mathematically, at each step, the Q of x sub t conditioned on x sub t minus 1 is a Gaussian with mean square root of 1 minus beta times x sub t minus 1 and covariance beta t times the identity matrix. So what happens is here over time the data becomes Gaussian noise, and to generate data the model learns the reverse process, often parameterized using neural networks. So this reverse process is trained using variational inference to approximate the data likelihood. By simulating the reverse denoising from random noise, the model generates realistic samples. So the diffusion process provides a robust and theoretically grounded way to model complex data distributions with high sample quality. Question 4. So the VAE loss function combines a reconstruction term and a KL divergence term. For Gaussian latent variables and Bernoulli or Gaussian outputs, the elbow becomes the difference between the reconstruction term and the KL divergence term. The reconstruction term encourages the accurate decoding, while the KL divergence term regularizes the latent distribution. About reparameterization trick. So to compute gradients through sampling, we use the reparameterization trick, which is z is equal to mu plus sigma times epsilon, where epsilon is the standard normal. So this what it does is this turns the sampling operation into a differentiable function of mu and sigma, allowing us to use standard back propagation to optimize the VAE loss. Question 5. So here is the list of all the papers that are given during the course and what I learned from each of them. So I'll just give few of the papers that were listed. Autoencoding, variational base, diffusion model, a comprehensive survey of methods and applications, conditional generative networks, unsupervised representation learning with deep convolutional GANs, hybrid norm towards stable and efficient transformer training. So DDP and denoising diffusion probabilistic models, deep generative image models with using Laplacian pyramid of GAN, the original paper for generative adversarial networks, and improved techniques for training GANs. So most of these covered the concepts of VAEs, diffusions, how noising and denoising happens, how VAEs work, and the extension of GANs to deep convolutional networks or conditional GANs, which use certain conditional settings, so yeah, these were the ones. 6. So Learning GANs, VAs, diffusion models, and transformers, in my opinion, is very important because they form the foundation of modern generative AI, and these models will help in a variety of applications in computer vision, NLP, healthcare, and all the other industries. GANs excel at realistic image generation through adversarial training, while VAs, they provide structured and interpretable latent spaces ideal for controlled generation and a variety of generations. While diffusion models, they produce like high quality outputs with stable training by gradually removing the noise. Transformers are like the backbone of NLP and vision systems. So personally, I feel learning these models has broadly improved my perspective as an engineer. Introduced me to it has given me some hands-on experience with techniques that go beyond deterministic programming, and these tools will add a new layer to my existing toolkit as a software engineer, allowing me to not just consume data but generate, manipulate, and reason with it. Tend to apply this knowledge in building AI augmented products or solving real world problems which have intelligent content generation, document summarization, etc. So my end goal is to merge my engineering experience with generative AI and grow into ML engineer roles, or as a software architect who can contribute to planning enterprise AI software.